Okay, good morning, everybody. Hope everybody's well. So we're still in this new realm. So I'm going to position my chat a little bit. Okay, so we're still in this new realm now of, no, that's not good. Okay. That'll be better. Reshare. Okay. Okay, so let's continue. So first, yeah, let's Marcelo put a reminder out already. The course evaluations are posted. They are extremely valuable for us to know how to proceed with the course next time. So use your altruistic self to fill out the course and make things better for your fellow students in the future. So we're going to continue our journey into parallel programming. Parallel programming is what we have to do if our computation basically is too heavy for a single core to do it. And in particular, this week and a little bit of the next week, we're looking at when it's too complicated to do on a single node. So multiple core machines are very common these days, but even they have their limitations, either because the memory is finite or just because the plain speed at which things are going aren't right. But we've also already experienced that we can't let the compiler just automatically use those cores. The compiler cannot figure out what's in your serially written code can be run in parallel or not. We have to say that. In OpenMP, we did that with Pragmas. In MPI, we're going to do that with a library. So that is more hands-on, and we have to do it with a library because well, first of all, there are some languages that can do this in the language, but they're not that popular. So this is the main programming paradigm for distributed parallel programming. But also because the memory is distinct, so each node has its own memory, there has to be communication by sending data over the network. That has to happen anyway. Even if it was somehow hidden from you, that has to happen. So in MPI, it's not hidden from you. You have to do it yourself. So we looked at point-to-point communications, and I showed this last time, but I want to go over it one more time because it is a different paradigm than the OpenMP. So we have basically three paradigms here. We have the serial code that just runs from top to bottom, and that's kind of how we think of programming. When you start, you just tell the computer what to do step by step, and it does it, right? Then we had threaded programming, so shared memory programming, where some segments were done by multiple threads at the same time, but they all saw or could see the same data. We have to say which data they could see, but that means that they can cooperate on the same data at the same time. We had to worry about race conditions, and so that's what we're doing in the assignment. One of the things that is tricky, but as soon as we do that, that's fine. But we still have one program with some parts being done by multiple workers. MPI is kind of the opposite way. You have to think of MPI as completely independent workers that just get up in the morning, and in the mail, they receive one number, the rank. They go, you're a rank, and they receive how many people have received that letter. And once they've gotten that letter with rank and size, they have to determine what they're going to do that day. And if they need some information from another person, then they would have to write a letter or send an email to that person and either send the data, and that other person has to be actively looking at their mailbox to receive it. Otherwise, it doesn't work. So it's an active messaging. That's not really the term, but it's both sides, senders and receivers, have to be actively involved in this message passing. So here was the code to send something to the right and receive it from the left. Yeah. So like any MPI program, it starts with MPI init. That's when these different people, the different workers, receive their letter saying that they are part of a group of workers. They have to then call the comRank and comSize functions from mpi.h to get their actual rank and size, but that the fact they can do that is initialized by this init. Okay, they're now part of what's called a communicator. They can now send messages to different ranks, and so they're going to send messages to the right and receive from the left. So if they know their rank, then message from the left, those people have rank -1, and on the right, that particular person would have rank +1, right? Except on the very end of this rank array, if you want. It's not really an array. If this turns out to be negative, there is no negative rank. Ranks start at 0. We can set this to MPI prop null. That says that if I ever send something to left or try to receive something from left, even though there's nobody there, it's fine. That just passes. It does nothing. Okay, that's an acceptable move if you want. Similar with the right move. And we're going to send a message. The message we're sending is rank times rank, so the square of its rank. And we're going to receive it in a variable, which we're setting to -999, just so that we can see when nothing has been received. But we're going to print it. If we see -999, we know that we haven't received anything. Then there's a send. The S send is for secure send. It makes sure that it basically tracks the message, and as soon as it's delivered, then it stops. And then there's the receive end of it. So we're sending to the right one double. This is a double. We're sending the pointer. Remember, this is a C program. It can send anything, but it can only send anything because we're giving it a pointer to the first address where things are stored that has to be sent. One double to the right. We're giving a tag. The tag was set to 1. It's kind of artificial, but we have to specify one. And then we have to specify what kind of communicator we're using. In all of our examples, we'll see MPI comWorld. You can split up your world in different pieces if you want, but usually that is not necessary. And then after we've sent our data, we're going to receive from the left. And then there's an additional variable, our status, that we can check whether or not the receiving was correct and how many doubles we actually got. It is even possible to send a message of 0 doubles. So if we could have received, potentially, if our code was written differently, a message that whose maximum is 1, but where we just received 0, and that would be in the r status, rstatus.size or something like that. And then we write out what was sent and what was gotten. Okay. So if we run this, it's called second message. MPI run it with 3 actors, 3 workers. So MPI run -n3, second message. That MPI run, remember, start 3 completely different processes that all run the same thing. So it sends 4 and got 1. It sends number 2 sent 4 and got 1. Number 0, so rank 0 sent 0 and got nothing because there was nothing to the left. So it's receive buffer or variable is still -999, and rank 1 sent 1 and got 0, and that makes sense. We can scale this up at any number of processes, and it just keeps on working. Obviously, the squares get bigger, but that's it. Okay, now that's fine. That works, right? And it does. You can go through the code and see what happens. You send something, you receive something from somewhere else. No problem. What if I had periodic boundary conditions, and I wanted to send the rank squared from, in this case, rank 2 back around to rank 0. So I'm sending to the right, but I have periodic boundary conditions. -n is the number of MPI processes, so the number of processes that I'm starting. So in a cluster context, a node has multiple cores. So you have cores; those are the things that can run. You could run threads on cores in a single node, or you could MPI process on cores. The node doesn't matter, but in the teach cluster, we have 16 cores on a node, so we could run MPI run -n16 and run on a single node 16 processes. If you use the debug job command and you specify the number of cores, you can do debug job -n16. You'll get a single node. If you do debug job -n, say 32, you get 2 nodes. So now, if you can do MPI run -n32, and you'll run on more than 1 node. So it's important to keep that distinction a little bit. We're talking about cores, so things that can run independently, and there's multiple of those on the node. So that's what it is. So 3 processes are started, and in this case, they'll be running on the same node, but they run as different processes, so their memory is still distinct. They can't see each other's memory. That's processes are shielded against poking in each other's memory by the operating system. Okay, so if we do this, we can implement periodic boundary conditions by just changing what left means. So left now means size -1 if we're on the very left end, and right means 0 if we're on the very right end. And other than that, you would think you just keep the same code, no? But no, that doesn't happen. If you try to run this, and I think it's called third message, and you do mpi run-n3 third message, it just sits there. You don't even get a prompt back. It doesn't do nothing. It just hangs. It's a deadlock. And it's a deadlock because of the following situation. In the code, we're sending first and receiving next. So every process is sending data, but it's doing an ascent. So it's waiting for that data to be received at the other end. But that other end is still waiting for its sends to be received by the other end, which is still waiting for the other end to start receiving, which is still waiting for. So we have a deadlock. Whenever you write down your communication pattern and you see cycles, you have a potential for a deadlock. Everybody's waiting on everybody. And so I've mentioned this before, when you're sending and receiving, there has to be a sender and a receiver. They have to be paired, but not only do they have to be paired, because in the code there is a send, there is a receive. They don't have to be just paired in the code, they have to be paired at the moment that the communication happens. Otherwise, you have a deadlock. Now, this must be fixable, because sometimes you need periodic boundary conditions, and this is what you have to do. So how do we fix this? And there's a couple of different ways. One relatively easy to understand way is to not all send and receive at the same time. Some processes are going to be sending at one time, and other processes are going to be receiving. So you could, like, if you had an even number of processes, you could do it this way, where you say the even processes are sending first. The odd processes, the first thing they do is a receive. And then there's a next step where the even processes are doing their receive and the odd ones are doing their sends. So we'd have an if statement there. We'd say if the rank is even, send first, then receive. Otherwise, receive and then send. If you do that, it works again, right? Because now at every step, at every time, we don't have closed loops. So so these two sends and receives actually even happen in parallel at the same time. So we have two steps, but there's really no way around it. We either have a deadlock, in which things take infinitely long, or we have two steps, which is a much faster process than infinitely long. Okay. Now, there is a MPI function that does pretty much just that. It takes care of breaking the loops, and it's called send receive. So we don't really care in this code which process does the send first and the receive first. We just want to break the deadlock. We just want to break the cycles. So we can ask the MPI library to do that for us. We can make a send receive where we combine the send and the receive calls, and basically have double the amount of function parameters then, and we just give them there. And send receive doesn't mean first send and then receive. It means it's somehow accomplish that a send and a receive have been done once I exit this function call, once the function call is done. And you, MPI library, you figure it out. So it's much nicer. It's just a single line, send receive. That's what I want to accomplish. And so rather than having to break the code into different if statements, which becomes even trickier if you have an odd number of processes, it's doable, but it's yet another if statement essentially. You just say, MPI library, you solve it for me. It's solvable. You know what is connected to what. You can figure this out, and it will do it for you. So very convenient. little function here, send receive. Any questions? Oh, Marcelo is remarking. That's not a question. Yes. Okay. So that's the pure sending of messages. If you need data, this is how you get it. Every process still will have to figure out what data it wants to send and wants to get based on its rank. But sometimes there's other communication patterns where it's not a point-to-point communication. It's not one rank to another rank. And one of those things is a reduction. We've seen reductions in OpenMP. That's when you have, say, an array of values. You want to add them up. You want to use, in that case, several threads to run to sum up parts of it and then sum everything at the end. You can do the same thing with MPI, where you could have an array that might be distributed over the different MPI processes, and each of them could be summed up, and then somehow we have to sum those values up again. That we could do that sort of manually and send, say, everybody's result back to rank 0, but the MPI has a way to do that, and those are the MPI reductions. There's a question from Michael. If you're asking multiple nodes, is it better to use MPI across the 2 nodes and OpenMP within the node, or MPI for everything? And that it's an optimization question, but it depends. You would think that you should always do OpenMP within MPI, but also within OpenMP, there's always serial sections. So you're starting threads and closing threads all the time, which is some overhead. So it really depends on the precise way that things are going. A lot of people these days, when they run at scale, they do a combination of both, but they make it a tunable parameter. So they just see, okay, for this machine, what is better? Do I run 2 MPI processes on a node and the rest is threaded, or 1 MPI, or all MPI? And it depends on architecture, communication patterns, memory requirements, a lot of different things. So often you write it as if anything is possible, and then you tune it. Okay, so back to the reductions. What kind of reductions can we have? Kind of makes sense. We can do things like take the sum of values. We can take the minimum of things, the maximum of things. So here's an example, and it's going to be a fairly lengthy example on purpose. I want to go through these steps quite slowly. But this is what we want to do. We're going to have an array of random numbers. They're random between -1 and 1. Okay. We want to compute from that array the minimum, the mean, and the maximum. If we have a large number of random numbers, we know that the minimum is going to approach -1, because at some point we're going to draw a number that's close to -1. The maximum should approach 1, and the mean should approach 0 as we take more and more numbers. Okay, but we're going to do this with MPI. So this array will actually be split in pieces. Each MPI process will have a subset of this array and compute its mean and max and minimum, and then use a reduction to compute the overall minimum, mean, and maximum. Okay. So I put the whole code on here. It's a bit monolithic, but that's partly to make it fit, and partly because sometimes going from top to bottom is somewhat easier to follow. So it's all one big thing, which I apologize for, but this is what it does. It's an MPI program. Okay, it's going to run several processes at the same time. Each process will need to know its rank and its size. So this first parse is almost always exactly the same for every MPI process. It's just setting it up, and then we know what each process knows its rank and how many there are. Okay. Now, I've hard-coded here. You usually have that as an input parameter, but I've hard-coded here that we're going to do, this is 200 million points. Okay, so nx is a constant. It's 200 million points that we're going to draw. We're going to draw, but here it's just a number, right? We just have how big is it? Because we're going to not want every process to store all 200 million points. One of the reasons to do MPI is that you might run out of memory on a single node. So we're going to imagine that 200 million numbers do not fit in a node. Of course they do in modern computer architecture, but suppose they don't, we cannot store then that array in a single process. Each of these processes is running simultaneously, right? So each process has to do the same thing. So we figure out how much each process should have, and each process figures it out. So they're all running the same code. They're all calculating how many numbers do I need per process. So nx per, which is computed here in a way that it rounds up. Okay, and that's useful because we don't want to miss any points. So it rounds up by adding size -1 and dividing by size. And then with integer division, that's a roundup. Okay, and then that's okay. Every process will take this many points, nx per, but because it's a roundup, would be too many. So the actual number that this particular process will have depends on its rank. If it's not the last one, we will take nx per. If it is the last one, we will take how many are left. So nx own is nx per, except for the last rank, where it's just whatever is left. If this is divisible by size, it works out the way you want it. If it isn't, the last one has a little bit less work, but really doesn't matter that much. Okay. Okay, so that's just numbers, right? It's just figuring out what I should do. As I said, it's like getting your letter, getting your rank and your size, and figuring out what to do on your own. What should you do? So it creates a vector that just has that size, nx own. It doesn't create the vector of size nx because all of them are doing the same thing. So that would be like way much storage than you want. And then we're going to run our random number generators. Now, we've looked at random number generators last time in a way where we took different seeds for the different parallel processes, and we could have done that here. It's a good approach. All you need is a different seed per rank. You could even use the rank as the seed. It's a little dubious whether that's random enough, but it might not be a bad first approach. We could also have some random numbers generated and then distributed. We'll look how that looks later, but we haven't covered that yet. So what we're doing here, though, is yet another way to go about doing random numbers in parallel. Because one of the things we know for sure in this case is how many random numbers each of the processes needs. We didn't know that for, say, the traffic model, because we are only running random numbers when the velocity is not 0. So sometimes it's 0. We don't know how many random numbers we need per process. So we couldn't do this approach. But in this case, we know exactly how many numbers there's going to be. So all we want to do is say, well, we have this array of random numbers virtually that has to be generated, and we just chop it up. And so every process should use the numbers in that sequence starting from an offset. So that's what this discard function does. So you can have a random number generator. Here it is, engine. I have a distribution drawing from -1 to 1. Remember, that was the actual task at hand. And I'm using not the Mersenne twister because it is actually very expensive to jump ahead. But the min-std is a very reasonable random number generator. It's not as good as the Mersenne twister, but it's very reasonable. And it can skip ahead. It can discard a certain number at a rate that is faster than linear. So so what I'm doing is conceptually, I'm generating nx per rank numbers and then continuing on from there. And because it depends on the rank, that gives me the offset. But it only does that conceptually. It doesn't really do it. It has a clever algorithm to jump ahead because of the type of random number generator. So as I said, they don't all allow this to be done efficiently. This one does. So now what I have is basically the same sequence of random numbers chopped in parts without any communication. I haven't communicated it again. This is again the same philosophy of each process gets its rank, and from that determines what it should do. Okay, there hasn't been any communication yet, apart from knowing where you are in the set of processes and how many there are in total. So after I know how many numbers I need, nx own, and I've initialized my random number generator to start at the right spot for me, for this process, now I just run and compute the random numbers in that I. So that is just to do that. You might imagine doing something else where you, if you had enough memory, you draw all of the numbers in process of rank 0. So there's an if statement. If you rank 0, do them all, and then start sending them off. And while that would be equivalent in terms of what you get out of it, it would not be as efficient because one of the ranks is doing a lot of work and the others are doing nothing. So it'd be a waste of ranks. And in fact, drawing random numbers is going to be the most expensive part of this computation. If you profile this, you'd see that you're spending most of the time in this part. So you want that in parallel. This is better performance-wise. Okay, so we've got our numbers. Now let's compute the minimum. If this were just a serial code, we could compute those three things. And we're computing the minimum, the sum, and the max here, and putting them in an array. I could have different variables, doesn't really matter. It helps to have them in an array a little bit for the MPI, but not necessarily for the computation. So I just run over all of the numbers, keep computing the minimum and the sum. I start these guys off with numbers that are so large that I know they're not a minimum or I know they're not a maximum. So that's a usual thing to do. And so at the end of this, I have the sum of all of the variables, the minimum and the max. It's easier to work with the sum than the average, because for the average, I just have to divide by the number of points at the very end. So I'll leave that to the end. So just do the sum. Okay, so that's computing that. Min, max, sum. Now I need to communicate. So one way to do that is to actually send it deliberately by hand, where I say, okay, one of the ranks is going to be collecting all of the information. That's going to be rank 0 here. That's collector rank. If I'm not the collector rank, I have to send my data to rank 0, to the collector rank. So I'm sending things. There are, in this case, 3 elements in this R vector. The pointer to the data in this R vector is mm.data. They're all doubles. Go send it to the collector rank. I give it a tag of 13 for no particular reason except the tags have to match in the MPI.com world. If I am the collector rank, I am going to have to receive size -1 messages, right? And so I'm going to run over. So I'm kind of using that the rank is 0 here. So I'm going over all of the other ranks from 1 to size -1 and receive their data. And once I've received the data, I'm going to update my minimum, maximum, and sum, so that at the end of the day, at the end of this block of code, rank 0 has the global minimum, the global sum, and the global max. And then I can write out the averages by doing the min, sum over nx, and max. And then there's the Mpi Finalize. You always need Mpi Finalize, or your program will crash. Even though it might have done everything successfully, but it'll crash with an error, and you go, what's this error? Well, you didn't finalize anything. The thing is, if you don't finalize, sometimes you don't get the right answer. The things might not have been printed, or because it might be that process 2 of rank 2 finishes in main first, and then tells, oh, I'm done, and everybody stops. It sends a signal to all of the other ones. They all abort, and you never, but you don't give a rank 0 a chance to write out its final result. So Mpi Finalize is something you should always have. So there's a question, what happens if all the other processes try to send at the same time? Yeah, and that's not a problem. And as you said, that's not because there is not a loop. So right now they're sending all at the same time. And that goes somehow into a buffer. And it is possible, if you had a lot of these, that buffer might overflow and then you get some error. But it's not because it's a deadlock. It's a matter of capacity. It might have been better to set this up, and it is possible, in a way that you don't care which of the ranks here is sending. In fact, that's already what I'm doing, right? See this MPI any source? That means that I don't insist that this message comes from each of them at the same time. So they're sending them. They might send them in different orders. I don't care. The order doesn't matter to get min, max, and mean. So whatever message is ready for me to receive, that's what I get. So as long as and if I'm not ready to receive that, because I'm using an send, in fact, that process will wait. So it's trying to send. The other side is not ready to receive yet. So say it's busy receiving another message, then this will just wait. So that's the nice thing about send. That's why it's more secure. You can't have these buffer overflows. If you just did a send, so there's actually a variant of this that does this, just send, there is a chance with a lot of messages that it overflows and the MPI library gives you an error and you don't know what's going on. Yeah, so this is a good question, Brennan. When does the splitting occurs? And the splitting occurs at the MPI run part. So there's no splitting in main, there's no splitting at file level. The whole thing is as if it's running separately. So let's see if you have the MPI run somewhere here. Yeah. So when I'm typing MPI run, it is kind of, imagine that these were 5 nodes. It's kind of like I logged into the 5 nodes, different terminals, and at the same time typed in each of the terminal 5th message. Okay, so there's never any splitting. Really, it starts off distributed, and that's something to get used to. It is a different paradigm, if you want. It's very useful to scale things up, extremely useful, and once you get used to it, it makes a lot of things easier to set up properly. But it is very different from thinking in it in a serial mode. Okay, now we've done this. It is not horrible. The reduction is working, but we still need quite a few messages, and they all have to go to, for some reason, it was the last one here. In the code, it was actually the first one that has to receive them all and add them up. Now, if we had a lot of messages, and we imagine that every one of them takes some time to communicate, say the time to communicate is CCOM, so that for one communication, then if I have p processes, I need p times that just to receive all of the data. Okay. And if I wanted everybody to know, this wasn't the case here, but if I needed everybody to know the total, I have to send p messages back. So that's 2p minus 1 messages that have to be sent. So the communication time would scale linearly with the number of processes. For 4 processes here, you're hardly going to see that this matters. But if you're really scaling up to 80,000 cores, say, this can become your bottleneck. And it doesn't have to be that way. You can do it more efficiently by doing subsums. So you could have core 1 and 2. Say core 1 sends its results to core 2, it sums it up. The same happens for the other 2, and then afterwards they sum up. And if you had a large number of CPUs, that would make a substantial difference in how much communication you would need to do and how long they take. Okay, so you basically change p to log p. Much better. You could code this yourself, but you do not have to. And if you do not have to, you shouldn't. So you code this up yourself. So you don't code up this yourself. There is an MPI call that does this for you. And these are called Mpi Collectors. There is an Mpi reduce and an Mpi all reduced. Those are 2 functions. Let's focus on Mpi reduce first. We want to reduce some variable. So there's a send buffer. That is the local thing that I have. But there's also a collector. It was process 0 for us. That's what this root argument is here. So that would have been our collector root, collector process rank. And that has to have a buffer. And the root itself can also have an element that has to be added up. So the root can have a send buffer and a receive buffer. Obviously, they're not really going to get sent, but it will copy that into the receive buffer. Okay. And then you have to say how many elements you're going to do. So you can do more than 1 element at the same time. In our case, we want 3 doubles to be reduced at the same time, but not onto each other. So that makes any sense. So it's like 3 channels that are summed. The type, which are going to be doubles, and the operation you want to use to reduce things. So you could have a sum, you could have a min, you could have a max, you could do a product. Other than that, there's not a lot that makes sense as an operator because it has to be an operation that commutes. If I change the order of things, it has to be the same. And the communicator. So this does this reduce call does exactly what we just implemented, but the MPI library can say, well, this is so many processes, I'm going to do a tree-based approach. You will never know that it does that. If you have a very good network, the MPI library might actually know that this operation can be done in the network. So there's very clever networks these days where as you are sending messages to nodes, two messages are coming in, that basically the interconnect card can add those messages. The CPU doesn't have to do that. So even more optimizations. There's no way you can get that without using the MPI library. So that's great. It works very nicely at scale. And it sends the results to a single process, root. The all reduce does the same thing, but sends the result back to all of the processes. So the receive pointer is going to be filled for all of the processes, whereas for the regular reduce, only the roots process will have the answer. Okay. So there's a question: can we add lines after Mpi finalize? You can. You cannot do any MPI calls after that. So you could print things after that. It is allowed, but the behavior is not defined by the MPI library. So what happens is a little bit up to grabs. Usually it works the way you think, but that's more heuristic than anything. So you can have a print statement after that saying I am done or something like that. But there's no real reason, right? Like when you're done, you're done. You can leave finalization to the end. There is not. It's also not allowed, for instance, to call MPI init again. So you cannot do a thing that looks like you're doing OpenMP, where you open with MPI init, you MPI finalize, and then you run MPI init and MPI finalize. It also means you can't have MPI init and MPI finalize nested in some sort of function call, because you would call it twice and the second time would fail because it's trying to reinitialize something that was already taken down. So yeah, exactly. So you cannot do it, but MPI init also doesn't spawn the other processes, right? It doesn't do the splitting. They already exist. They're already there. Now you just tell them that they're part of a bigger group. And the finalize says, in some sense, everybody is done. You don't have to bother receiving any messages ever again. Basically, it says you're fired. You can't rehire them. That's, think about it that way. All right, so let's use this process then. And in the code, the little part that did all of the communication, not so little, the part that did all the communication becomes a lot more streamlined. We just create one vector that will contain the answer. In this case, let's say that everybody wants to know the answer at the end. We do a global MMM. So the MMM was containing the local min, max, and what will be the mean. And so we do an all reduce for the mins, for the max, and the sums. Now I can only specify one operation at a time, unfortunately. So that's why I still need 3 calls rather than one. But in any case, that's what it is. Okay. So I'm taking the address of where what goes in, the address of where it goes out, one double, take the minimum within com_world, and then max and sum are the same. And then I print it out only if I'm rank 0. Very similar to a reduction variable in concept in OpenMP, but very different in how it actually looks in the code. Now, this is not the only collective operations. So this is called a collective operation because everybody in Mpi com_world is taking part in this process. There's other ones which are collective, which involve everybody. And whenever it involves everybody, if you coded it in yourself as pairwise interactions, pairwise messages, there's a good chance that you might end up either with a deadlock, or like we said with send receive. Send receive is not collective, but it involves 2 processes kind of collectively. If that makes any sense. But you could get a deadlock, or you could do it inefficiently, like sending way too many messages in a serialized version. Okay, so you don't have to know that. For the following cases. So one of the other MPI broadcasts is collectives is a broadcast. It's MPI_bcast. You can look up the exact syntax, but what it does is one process has a value and sends that same value to all of the other processes. So rather than doing it one by one, it just says broadcast it to everybody. You'd often do that with parameters, for instance. The root process might be reading in the parameter file and then sends those parameters to all of the other ones. So you don't have to touch that file from everywhere. Scatter is similar, but here you start with an array. This only works if you have enough memory to store this array in one process, but you could imagine sometimes it might be useful to read in an initial array, for instance, and then split it up and scatter it. So this looks OpenMP-ish, but it really isn't, because this first array is in one of the processes. So this is a memory-heavy process, and these other ones are not, or 0 still takes part. So 0 is sort of has 5 elements, the other one has 1. So it's really unbalanced. It's not great. You use it sometimes, but you know, it's not that distributed in memory. You distribute sort of more dynamically. There's a variant that basically takes it upside down. You have your data in your different processes, and you gather it. This can sometimes be useful when you want to do I/O. We know I/O is slow from our I/O lectures. You could do a gather into a single process and have just that process write out. Again, there could be memory issues. There could be it could actually be faster if you have a parallel file system to just write from the different processes. But if you do need to gather things, there is an MPI gather for it, and it makes sure that things don't deadlock and that it's fairly efficiently done. There's other MPI collectives. File I/O, there's actually a whole bunch of MPI I/O calls, which we'll see next week a little bit, that you can use to do this sort of I/O in parallel. There's barriers that say all processes have to wait until we are here in the code. You should never have to use those except in debugging cases. So in debugging cases, you might want to know that everybody hits a certain point in the code. That might be useful. But other than that, whenever a process can continue, it should. Why keep it back? If there's any reason to keep it back, you probably missed a message dependency or something. And then there's all-to-alls, which are kind of like scatters and gathers, but every process scatters some stuff to other processes. And as you can imagine, that is very communication heavy. And again, something that you tend to want to avoid unless you can't. If you're doing multidimensional Fourier transforms and use FFTW, which actually has a MPI version to it, you're going to have it under the hood. Will have to do something like an MPI all-to-all, but you know, be careful using those. All right, let's look at an example. I think we're only going to start this here. We have 4 minutes left, and then we're going to try and continue it next week. But I want to go to an example that is a little bit more scientific computing-like. So we're going to look at a diffusion equation. And so we've seen this a little bit in the partial differential equation lecture. And we're going to use a finite difference time marching method. And we're going to imagine that we have too much memory, too much data. Our grid is very fine, and the grid doesn't fit on a single node. So we must do MPI. Okay. What we will do is what's called domain decomposition. So we'll take our domain, right? It'll be a grid, and it'll be solving this partial differential equation, so diffusion equation, by doing a discretized version of the derivatives, kind of like this. So T is my field here. This is an array, and the second derivative can be approximated in this fashion. So we have a stencil, basically. I need neighboring cells values to compute the second derivative at I, and that's what we do. So we take the simplest one here. There's more complex stencils. These are called stencils that you can use to compute the derivative to higher accuracy, but we're going to stick with the simple one. Okay. So we can do this in higher dimensions as well, just a different stencil. I don't know why the equations aren't popping up. Okay, so this is a very common thing that can happen. Oh, here. So whenever you have a large simulation box, a fine grid, you're going to want to do this domain decomposition. And so before I go to the technical details, let me stop at showing some examples. So say you wanted to know the flow of a air around an airplane. You wanted to simulate that rather than build the airplane, put it in a wind tunnel and say it's no good, and then start building an next airplane. So simulations, CFDs, computational fluid dynamics, are extremely important in airspace aerodynamics design, because there's a lot of designs that you can discard doing a simulation without having to build the actual plane and put it in a wind tunnel, or say just the wing even, right? There are simulations. One always tests after finding a good candidate in the wind tunnel whether it is really doing what you expect, and then there's a whole bunch of tests. And that is not the only thing you do, but if you do it, you typically have way too many elements here, like these are fluid elements, then you can tackle in a single node. So you divide it up. You say, well, some parts of the domain are for one process, another part of the domain, another process, etc. But obviously, just as in the case of the diffusion equation, you're going to have communications across the boundaries of these domains. The same is true if you do molecular dynamics, for instance, right? So if you have molecular dynamics simulations, and here it's a very regular grid of atoms, say, the different parts will be able to move out of their domain. So these are particles now, they move about. You might have to do a similar thing that we did with the periodic boundary conditions. If you move in one way, you have to put it back at the end. In this case, if it moves one way, you have to put it in the set of atoms that the next process or the neighboring process has. So it's a little trickier to do, but it's still a way to do domain decomposition. You decompose physical space in some way, and make sure that only the things that are in that space are part of what that process does, and then you deal with whatever communication you need to do to make the computation correct. Similar for n-body simulations, but in those cases, you often have way more inhomogeneities. So you have some parts that are very dense and others that are not. So your subdivision of space should be way more fine-grained and dynamic, such that you have roughly the same number of computations to do per process. Otherwise, one process will be still doing most of the stuff, and the other processes are just sitting idle, having already computed what happens in empty space, namely nothing. Similarly, for climate simulations, if you want to simulate climate over the whole Earth, you're going to have to cut up the Earth in little pieces. And that sounds like a lot of fun, but you still have to communicate among those pieces. So here I took 6 pieces and I laid them over a cubic sphere basically. But there's communication here, right? Just as in the diffusion equation, there's going to be boundary cells. But that way you can scale up. You can make your grid finer, use more nodes, and get some scientific computations done. So in each of these cases, there might be load balancing to do to make sure that the computational load is the same for every process. There'll be communications back and forth. So that's something to do explicitly. One of the things you want to try to do is sort of maintain locality. That is to say, points that are close together should be in the same process as much as possible. That minimizes how much communication you need to do. Communication is more expensive than computation. So the fewer communications you can do, the better. So that's sort of how you would program this. That's why domain decomposition kind of works. You could also just say, well, let's just randomly assign different atoms here to different processes, and you would have decomposed the data, but you'd be doing a lot of communication to make up for the fact that you did it wrong. So I'm going to stop here, and then next time we can look at how you actually do this for a simple case like the diffusion equation to get an idea of how things are going. Any questions? Yes, there are debuggers specifically designed for MPI. Wilson asks, and yes. So most of those are commercial. You can do threaded debugging in GDB, believe it or not. This is doable. But we have a debugger called DDT. So you type module load DDT, and then module load DDT, and then you can load the DDT debugger. And so that we already talked about DDT, but it can do MPI. It can do threaded. It can do GPU programming, which we'll touch upon next week. But that's yeah, it's a powerful debugger. It's tricky to get these things right, so there's nothing that really scales up that is open source. Before we had DDT, what I used to do to debug MPI processes is to open. I'd have a script for it, but to open, say I'd have to debug a 32 process MPI process. I'd open 32 terminals, make the font nice and small, and scale up the terminals, line them up, and then there's a way to start your MPI process, but sort of have it wait at int main. So I would do that. I put a little specific thing, and then I would attach a debugger to each of the different processes by hand, and then I would have 32 terminals and would have to step through each of them separately. And that is no way to do it, I can tell you, but I had to do that before parallel debuggers like DDT. There's other ones, there's Total View, and there might be one or two more that can do it, but it is a specialized thing so Finite has licenses for DDT up to 64 processes. So if you ever have to do it, just use Finite. Yeah, it's almost as bad as print statements, exactly. There's one other question. The discard, Brendan asked. Let's go back. It's a good question. So we've got, say, 4 processes running this code. Right? They're all doing the same thing. They figured out how many points they want. They are all initializing the engine here with seed 14. But then if I didn't do the discard, each process would be drawing the exact same numbers, which means that I'm not drawing more numbers. I'm really drawing what is it, 50 million numbers really, and that's all I'm getting. So my sample is not correct. So what I'm doing with discard is saying I'm going to draw this many random numbers and not use them at all, so that the next time I draw a number, it's a fresh one. Okay, and because I'm jumping ahead nx per times rank, for rank 0, I'm starting at the start, right? And I'm only going to draw nx per numbers, so that's great. I'm not going to step over the ones that rank 1 needs. Rank 1 gets here and says, hey, I'm going to step over nx per numbers, which means it starts now nx per further down the road in the virtual array of random numbers, the array never actually exists, and that's the right spot for it to start. Rank 2 starts nx per even further along, etc., etc. So they just get different subsections of the stream of random numbers by doing the discard. Next. Okay. Any other questions? Oh, the assignment, we're going to probably post it either tonight or tomorrow. I know it's a holiday, so the posting date is a little bit funny, but we'll have to see. The deadline is probably going to be just a Friday, where I guess we never got around to going back to Thursday, unfortunately. But that's going to get posted. A few of you have a good idea of what it will be already, so